how fast is the material going to redistribute temperature as a consequence of this heat flow. And the redistribution of temperature does not go with the heat flux, but with the gradient in the heat flow. Now here's why. Imagine we have a linear system here. This box is T3, this box is T2, this box is T1. And let's focus in on the evolution of T2. Well, into this box, we have heat flowing in from over here at T3. Then we have heat flowing out in the box at T1. If the heat flowing in and the heat flowing out were the same, there would be no accumulation of thermal energy at all in this middle box, and its temperature wouldn't change. So the only way the temperature in the middle box is going to change is if the flux in is different from the flux out. In fact, the accumulation of thermal energy with time in the intermediate box is going to be the flux in minus the flux out. And of course, this is JQ is a flux per unit area, so I don't know about dA. You heard about it. Well, what would these quantities be? If I assume that the heat flux is a continuous function of the temperature, which is changing continuously over this region, then the heat flux at this point, at the 1,2 interface, is equal to the heat flux at the 2,3 interface plus the change in Q with respect to x times dx. This is just the relation between the two. So if I just plug that into my little equation down here, I get that the rate of accumulation of thermal energy is minus the gradient in the heat flux times the element of volume dV. This is dx times dA of dV. Well, since JQ is, from the previous slide, minus k dt dx, this is the derivative with respect to x of the quantity k dt dx, or if k is a constant, is k d squared t dx squared. Well, what I'm really interested in is not the accumulation of heat. I'm really interested in the temperature. So how are these two related? Well, the change in Q with respect to time is the change in energy, this is the thermal energy, which would be equal to the specific heat times the change in temperature with respect to time times dV, because the total energy content is energy per unit volume times dV. If I just plug this in, I get Fick's second law, which is the change in temperature with respect to time at some point in the material is the thermal conductivity divided by the specific heat times the second gradient of T with respect to x squared. And these are the two laws that govern thermal conduction. The diffusion flux response to the temperature gradient is governed by the thermal conductivity. The change in temperature response to the curvature, if you want, the gradient of the temperature gradient, is governed by the material property K over CD. The thermal conductivity divided by the specific heat at constant volume. See, I'm doing on time. Okay. To understand heat conduction in materials, we've already talked about the specific heat. We know all about that. So now what we have to do is focus in on this thermal conductivity. What is that? What controls it? Well, before I do that, let me just for a moment talk about 3 dimensions. If we're going to transfer these models into 3 dimensions, then of course our temperature gradient now becomes a vector gradient, gradient of T, which has components in the x, y, and z direction in general. The response will be a vector flow, which will have components in the x and the y and z direction. The relation between the heat flux and the temperature gradient in general will involve 9 coefficients, because each coefficient of J is in theory influenced by all 3 gradients in T. So I need 9 coefficients to connect these two. However, the symmetry of the material places very strong restrictions on how many of those 9 coefficients can actually be independent, how many thermal conductivities the material can have. And in the materials that we care about, which are cubic or isotropic, cubic material has a cubic crystal structure. An isotropic material is, for example, glass or amorphous solid or a polygranular material. If I have a material that contains many grains but randomly oriented, it behaves as an isotropic material. If the material is cubic or isotropic, it turns out that we only need 1 thermal conductivity. And the heat flow vector turns out to be parallel to the gradient in temperature. The proportionality is just K as before. This should be a K over CV. I'm sorry, this should be K over CV. The second law, the second gradient of temperature. Only 1 thermal conductivity. As a simple counterexample, suppose we have a hexagonal material. In a hexagonal material with hexagonal structure, the axis perpendicular to the basal plane along the axis of the hexagon is clearly different from the behavior in the basal plane. So we'll need 2 thermal conductivities to describe that. One for thermal conduction perpendicular to the basal plane of the hexagon, the other for thermal conduction in the basal plane of the hexagon. And more complicated crystal structures may require even more. But we'll stick with cubic or isotropic materials. Okay, where is the thermal conductivity coming from mechanistically? Well, we begin by dropping by and asking ourselves, what is there in the material that can carry energy, that can conduct energy from one place to another? What is there in the material that has energy? Well, in fact, there are 3 things that can happen in the material to conduct energy. One is electrons can move. The electrons are particles, they have kinetic energy, and if electrons move from one place to another, they will carry their kinetic energy with them. So I can conduct heat by moving electrons. Lattice vibrations, phonons. Lattice vibrations have energy, as we saw in discussing the specific heat. So if lattice vibrations travel through the material as traveling waves or phonons, they will carry heat along with them. Finally, photons can conduct energy. If I have light emanating from one part of the material to another part of the material, it is produced here, absorbed over here, then those photons carry energy, and that can be a source of conduction. We won't talk about photons. They are important actually in 2 places in materials. At very, very high temperature, because the photons are really excited, you can get a significant photon contribution, optical contribution to thermal conductivity. Ironically, the other place you can get a big optical contribution, and I just mentioned this in passing, is at very, very low temperature. If you go look at people who are putting together superconducting magnets, for example, the big ones, that have to operate at 4 degrees Kelvin, and you go look at the insulation in those superconducting magnets, you'll observe that the vacuum seals, the insulation on the vacuum seals, is always very shiny. The reason it's shiny is to reflect photons. The reason you have to reflect photons at low temperature, even though the photon energy doesn't sound like much, is that as temperature goes to 0, the specific heat goes to 0. Which means that when you're down at very low temperature, just a tiny bit of deposited energy can make a big difference in your temperature because the specific heat is so small. So when you start doing the insulation for deep cryogenic systems like superconducting magnets, you've got to worry about any potential source of heat, and that includes photons. So you have to make reflective insulation so you can bounce the photons back again. And if you look at a wrapped magnet, for example, going into an accelerator or something of that sort, you'll always see the shiny insulation around it. Well, yeah. Anything you're trying to get in the system, you want to bounce back out. You do not want to absorb photons from anywhere. It's shiny on the outside. Shiny looking at the photon source. But of course, most things are shiny on the outside or shiny on the inside as well. I'll give you another example. If you look at a piece of tinfoil, aluminum foil, you know it's bright on one side, dull on the other. You know why, right? When you wrap a turkey, okay, you want the dull side out so it absorb heat. You want the inside shiny so it reflect the heat back and keep it in the turkey. Had a PhD student some years ago, before being a PhD student, was actually a director of an alloy development program for Alcoa. He used to get furious. He said, you can't imagine how much trouble we go to make aluminum foil with one shiny side and one dull side. And not only does nobody know why, nobody even notices that's the case. And they put all kinds of effort into doing that. That's right. Yeah. Well, we're going to talk about that specifically. Okay. The electrons and phonons we can kind of handle together, at least formally, because quantum mechanically they're particles. So let's just imagine conduction by gas of moving particles. That's, for example, if you just have gas. Suppose we just have gas of atoms, and we're conducting heat down the gas of atoms. That's a gas of moving particles. Well, our particles are going to move both to the left and to the right. Both sets of particles are going to carry energy with them. So our net flux is our flux to the right minus our flux to the left, JQ plus minus JQ minus. The particle energy increases with the temperature. So if we have a gradient in temperature, and we've just got a bunch of particles, imagine gas here, the particles on the left where the temperature is high are going to have more energy than the particles on the right where it's low. And as the particles on the left move to the right, they will carry that energy, and they will carry more energy than the particles on the right moving to the left. So just imagine a gas and a temperature gradient. And you've got excited particles over here, less excited particles over here. They intermix. The net result is a transfer of heat from the high temperature region to the low temperature region. And that's basically what's happening if we just replace those particles by electrons or phonons. Transport of thermal energy. So let's assume the particles reach thermal equilibrium by collisions, whether they're electrons, phonons, or particles in a gas. The particle travels some distance L, a mean free path between collisions. And therefore, what's going to happen is that the particles up here on the left-hand side will equilibrate at whatever temperature they are. Then having equilibrated will travel a mean free path to the right. The particles on the right-hand side have equilibrated down here at lower temperature. Having equilibrated will travel a mean free path to the left. So we can draw any plane here and we can calculate the net transport of energy across it, recognizing that the average atom that crosses the plane equilibrated by collisions at roughly half the mean free path, either above or below it. So let's just do that. Don't get too carried away with this mathematics. I'm just going to sketch through what it is. To get this, suppose we're interested in the particles that cross this plane located at x. Those particles, if this is the positive x direction, the particles that cross at x were equilibrated roughly at a position x prime, which is x minus Lx, the mean free path. So these particles were equilibrated up here. So the temperature up here is what determines the energy of the particles. They now move forward. Well, how many move forward? The number that cross this plane at position x, well, the number of particles per unit volume, the energy per unit volume, times Vx, and one half of these will have positive. The velocity in x direction is equally likely to be positive or negative. So half the particles moving in this direction. So this gives me the total energy per unit area coming in the positive direction. Well, this NE is the energy per unit volume at the temperature T at which they equilibrate. And that temperature is the T at the position x minus the mean free path. So we get this expression. Then we use a Taylor expansion. EV Tx minus Lx is equal to the energy per unit volume at x minus the partial d with respect to T, dt dx times Lx. This is just a Taylor expansion keeping the first term. And that gives us this expression. The E dt is C dt. Just plugging that in, I wind up with an expression that the flux in the positive direction, this direction, is 1/2 the energy per unit volume right here times that velocity, minus 1/2 specific heat, velocity in the x direction, mean free path, the temperature gradient. Well, not to confuse you too much with the math, but now let's plug that in and write the net flux is the heat in the plus direction plus the heat in the minus direction. The flow in the minus direction is just it's the same thing, but now with a plus sign instead of a minus sign. When I take the difference, I get the JQ minus the specific heat, the velocity in the x direction, the mean free path, dt dx. And that gives me the thermal conductivity from a group of particles that equilibrate by collision with one another and have a specific heat CV and an average velocity df and mean free path Lx. That thermal conductivity is a specific heat times the velocity times the mean free path. In 3 dimensions, because we do have conductivity in 3 dimensions, we can just sum the 3 directions. And you end up with an equation that you'll see in virtually any solid state physics book or such, which expresses the thermal conductivity as 1/3 the specific heat, the average velocity v, the mean free path L. Or 1/3, another way to express this, I can also write the mean free path as the velocity times tau, where tau is the time between collisions. So I can also write it as 1/3 the specific heat, the velocity squared, times the mean time between collisions. And this is the equation you get. I'm sorry for going through the derivation very quickly. If you trace through the math even on here, you should be able to do it a bit more slowly. But this is the kind of universal expression for the specific heat, the thermal conductivity you get from transport by a gas of particles that equilibrate by collisions with one another. And that includes particles in a vapor, that includes electrons in a solid, that includes phonons in a solid. So here's our expression for the thermal conductivity. Now let's talk about the individual mechanisms by which that can happen. Well, here's the thermal conductivity by particles. So our final result for particle conductivity is, this is Fourier's first law, thermal conductivity. Fourier's second law, thermal conductivity divided by specific heat. Thermal conductivity, 1/3 mean particle velocity, mean free path, 1/3 CV times v squared times the mean time between collisions. Now let's talk about electrons and phonons. The easy one to talk about is the motion of electrons, electrical conductivity. If I just plug in the right expressions here, and I won't do the derivation, I'll just show you the result. The average electron velocity is the average velocity with which they're moving in the material. The mean free path, or average time between collisions, can be estimated. And what you can kind of immediately realize is that the phenomena I'm describing here, the motion of electrons, is precisely the same thing that goes on when the electrons are conducting electricity. So you would assume that the thermal conductivity would be proportional to the electrical conductivity. And in fact, it is. The coefficient of this is called the Wien-Franz law. The thermal conductivity goes like a constant times the electrical conductivity times the absolute temperature. Well, the electrical conductivity is the reciprocal of the resistivity. So I can also write it, thermal conductivity is a constant times the absolute temperature divided by the resistivity. As the conductivity goes up, electrical conductivity, or resistivity goes down, the thermal conductivity goes up right along with it. Because the easier electrons can move, the easier they can conduct electricity, and also the easier they can conduct heat. So this is the Wien-Franz law. Now this has, interestingly, 2 easy limits. It's a very simple behavior. Because the electrical conductivity can be written to a very good approximation as ρ0, a limited value at low temperature, plus a constant times the absolute temperature T, ρ0 plus AT. Plug that in, and at low temperature, where T is almost 0, I'm going to get a conductivity that increases linearly with T and is equal to LT over ρ0. At high temperature, where ρ is AT, the temperature is going to divide out, and I get a constant value of the thermal conductivity, which is just equal to L over A. So the actual behavior of thermal conductivity is very simple. At low, it's always just goes with the reciprocal of the resistivity. At low temperature, it increases linearly with temperature. At high temperature, it reaches a constant, which is related to the constant in the thermal conductivity L and the constant in the thermal constant in the resistivity A, just L over A. Well, the thermal conductivity is simple, and you can immediately decide which materials are going to be good thermal conductors, assuming that they conduct by the means of electrons. Those things that are good electrical conductors will be good thermal conductors too. And you can make an easy measurement. Just think of the various metals you can touch and which ones feel colder. Copper, silver always feel very cold, great conductors. Iron feels not quite as cold. Cold steel is not as cold as cold copper. Other things that are not good conductors very often don't feel cold at all. Glass, for example. Ceramic. Why do you use ceramic cups to hold your hot coffee? They don't heat up. Try drinking coffee out of silver cups. In Russia, for example, it's very common to serve hot tea in silver cups. I'm not quite sure why, because it scalds your lips every time you try to drink out of them. Nonetheless, they do that. Let me just say a quick thing about heat conductivity by phonons, because it's tough. For almost all the materials in the world, heat conduction by phonons is negligible compared to heat conduction by electrons. In ceramics and most insulators, glass and so on, you just don't get much thermal conductivity. You have no electrical conductivity, so there's no electrical conduction. Phonons don't do a very good job of conducting it. I'll explain why in the next period. There are, however, certain materials, diamond being the classic example. Well, the reason that you have lousy thermal conductivity is that phonon conductivity kind of varies like this for a crystal, where this is the Debye temperature. Once you get to the Debye temperature, and in fact this graph is a little bit wrong, we should get it lower there. Once you get to the Debye temperature, the phonon conductivity is essentially gone away for reasons we'll talk about next time. However, well below the Debye temperature, you can get a very significant contribution from phonon conductivity. So about the only place you're going to get significant phonon conductivity at any temperature you care about is in a material that has a very, very high Debye temperature. The world's classic case is diamond, whose Debye temperature is up around 2,000 Kelvin. At room temperature, the thermal conductivity of diamond is huge. And it is huge because phonon conductivity can be very high. Electric conductivity is essentially zero. You'll get a good jeweler, tell him to tell a real from a fake diamond. Well, the first thing to do is touch his tongue. A real diamond is cool to the tongue. Zirconia is not. I'll tell you why next time. Okay. Oh, class on Wednesday. Let me re-announce there'll be no class this Friday. And we'll be tied up.